Hello everyone. In this presentation, I'll be covering a recent CVPR 26 paper, Attention Surgery, an efficient recipe to linearize your video diffusion model. The ITs are proven as a dominating architecture within the video diffusion models. However, the quadratic complexity of self-attention poses a significant bottleneck. For instance, in VAN 2.11.3 billion, at a modest resolution of 480p, roughly 76% of the compute burden is associated with self-attention, while this proportion becomes even more overwhelming with higher resolutions and longer videos. Linear attention has appeared as a more scalable alternative with linear complexity thanks to a reformulation of a similarity as a dot product of two decoupled projections that results in terms that can be pre-computed. An even nicer property is that it is shown that the causal linear attention can be rewritten as an RNN where the memory remains constant regardless of the number of tokens. However, unfortunately, many studies have shown that the linear attention is underexpressive. To mitigate the aforementioned issues, in this work we present attention surgery, offering a lightweight recipe to turn a pre-trained state-of-the-art softmax attention model into an efficient hybrid model that combines the efficiency of linear attention with expressiveness of softmax. We show that by introducing learnable kernels for a linear attention branch and a blockwise distillation pre-training followed by a lightweight end-to-end fine-tuning, we can obtain an efficient hybrid model that is competitive to the original model under very modest training compute requirements. Now let's dive into the proposed hybrid attention model and the distillation process. For a given query token I, we separate the source attention tokens into a smaller uniformly subsample set to which we attend with a more accurate but costly softmax attention, and the rest majority that we attend to with a more scalable linear attention. Once we have the token separation mechanism specified, we define a hybrid attention comprised of softmax attention terms and linear attention terms. With the hybrid attention defined, we introduce our attention distillation process in which we target learning the phi k's and phi q feature mappings for each block independently, where the teacher is softmax attention and the student is a hybrid model, either matching their attention affinity matrices or directly matching the attention output values. Now let's look with more details into the learnable mappings, phi k and phi q. We define phi as a D-layer MLP with a degree p polynomial formulation. This design targets to first address the lower transformation rank and expressiveness of the original linear attention that uses non-learnable LU plus 1 definition for phi, and second, facilitate approximating the large dynamic range of exponentials with incorporated polynomial formulation. Here we see in more details how our attention distillation pipeline looks like. For a pair of sample prompt and initial noise, we cache the pair block and pair denoising step trajectories of a teacher model that are used then for a number of iterations to match the corresponding activations in the hybrid student. The obtained gradients are then used to train phi k and phi q parameters of the target distilled block while all other weights are kept frozen. Note that the distillation process doesn't require any video datasets and rather relies on textual prompts only. After the pair block distillation, we fine-tune the full model with flow matching for a small number of iterations, for example, just 1,000. Defining a hybrid rate as a uniform subsampling ratio of the softmax tokens, here we see qualitatively how the generated samples look like under different numbers of blocks converted to hybrid attention out of 30, with various hybrid rates right after the blockwise distillation pre-training and before the end-to-end fine-tuning. We observe that different blocks exhibit non-uniform error residuals due to the hybrid formulation under various hybrid rates. Furthermore, the compute complexity is a nonlinear function of the hybrid rate. This alludes to an opportunity to optimize a heterogeneous hybrid architecture with various hybrid rates, given the characterized residual errors and the corresponding cost. So, under a compute budget, we can frame this as a constraint optimization problem that can be solved efficiently as a multi-choice knapsack. As an overview, our proposed recipe comprises of 3 steps: a layer-wise distillation of softmax to the student hybrid attention to learn the phi transformations, optimizing a heterogeneous hybrid DIT architecture given the error residuals from step 1, and a lightweight end-to-end fine-tuning. As we observe with quantitative evaluations on vBench, various variants of our model offer a notable reduction in the compute while mainly preserving the generation quality. Also, our method performs quite competitively as compared to the state-of-the-art efficient diffusion models and the underlying VAN model as evaluated on vBench and vBench2 benchmarks. Furthermore, a method-blinded human preference study with more than 500 paired comparisons showed that in 70% of the cases, our results are visually equal or better than the baseline VAN model. Ablation studies demonstrate the effectiveness of our various design choices, including the blockwise distillation pre-training in our training recipe, the heterogeneous hybrid architecture optimization, and explore the space of linear attention phi projection architecture. We also observe that the proposed hybrid attention has a significantly better scaling behavior as compared to the original softmax attention and can run much more efficiently on mobile devices as assessed on Snapdragon 8 Gen 4. And we end up with a set of qualitative video samples generated by our methods. Thank you very much for your attention.